So we now look at another data structure called a search tree. So to motivate search trees, let's consider the following example. So supposing you are an air traffic controller and you're controlling access to a single runway where flights have to land and take off. So the air traffic control tower receives requests from the aircraft about their expected arrival and departure times. And these requests come at random times. So it's not that they come in order of the time of the actual event. So we might first get a request for a landing in Chennai at 16:23, and later on we might get a request for a takeoff at 16:12, which is actually earlier. And then we might get another arrival information at 16:55, and then another earlier arrival information at 16:18. And the strategy that the control tower is supposed to follow is to give priority to the flights with the earliest usage time. Right? So this is a priority queue. Each request goes into the queue, but it has a priority depending on the expected time that it's going to take place. So we could give a min heap representation. And if we take these 6 requests in the order that they come and we insert them into the min heap, then we will get the min heap that we see on the right hand side. Right? And so in this, because 1612 happens to be the earliest event among these 6, it will automatically float up to the root, and so it will be available to us as the next event to process. And then maybe 2 minutes before that event happens, we can send a signal to the flight giving it clearance to take off. So suppose we have an extra requirement on this. Not only do we want to give priority to the earliest event to happen, but we also want to impose some minimum separation of planes to avoid any possibility of collisions on the runway. So we say that 2 planes accessing the runway must be a minimum of 3 minutes apart. Now in this example, we can see that the rule is violated by the 2 events at 16:53 and 16:55. So what happens is that we should, when we insert or we accept the request for 16:55, assuming it came after 16:53, at this point we should check that whether it is at least 3 minutes apart from all the current pending requests. If not, we should send a message to the pilot saying 16:55 is not possible. You must move your takeoff or landing to 16:56 or later. Now, unfortunately, in the heap data structure, there is no easy way to do this. So when 16:55 is added to the heap, we have to scan it against all the elements in the heap in order to find out whether it is within 3 minutes of any of them. So this would be a linear scan. So all other operations, insert and delete on a heap, were logarithmic, but this, if we want to impose this constraint that no 2 elements in the heap are within 3 minutes of each other, then we would add an extra linear time cost to every insert, and this would then make a heap unviable for this kind of data. So one way to compute this kind of requirement is to be able to check the predecessor and the successor. In other words, given the list of values that we have, for any value, can we quickly compute what is the previous in terms of the nearest smaller value and the next successor, what's the nearest bigger value. Right? So if we look at 1618, for example, then the next smaller value is here, so this is the predecessor, 1612, and the next bigger value is here, so this is the successor. Now this happens to be, it looks like there is some nice relationship within the heap in terms of the tree structure between predecessor and successor, but if we look at a different value, for example 1653, then we'll find that the predecessor lies in a different branch of the tree and the successor lies in the same branch. Okay, so there is no direct relationship between the tree structure of the heap and the predecessor and the successor relation that we need. However, the important thing to note is if we could compute predecessor and successor, then we can solve this problem, because once we look at the successor or the predecessor and we find something which is within 3 minutes, then we can flag a warning and signal to that aircraft that that request is not tenable. So if we want to maintain this information, let's try and look at the different data structures we have seen so far. Okay, so we have unsorted arrays, sorted arrays, and min heaps. Okay, now in this particular structure, we are not going to look at directly a delete min or a delete max, but 2 separate operations, one which checks the minimum and maximum, okay, and one which deletes an element arbitrarily. So for min and max, as far as min and max go, okay, then it is clear that the best data structure is sorted array because these values are at the extreme ends of the array. The worst is an unsorted array because they could be anywhere and both require linear time. And then depending on whether we have a min heap or the max heap, one of them is good and the other one is bad. So in a min heap, we can find the minimum with the root, the maximum could be anywhere. And likewise in a max heap, the maximum would be at the root, the minimum could be anywhere. So if you look at the next set of operations, this is insert and delete. Okay. Now here it turns out that an unsorted array is good for insert because we can just stick it in at the end. For delete, we have to go through the array and look for the value and remove it, so it will take linear time. In a sorted array, both will be slow because we have to either insert in the correct position like an insertion sort, or when we delete, we have to compress the array, which will take linear time. Now we know that in a min heap, insert is logarithmic. Okay. Delete is also logarithmic, even though this is not delete min. Okay. So this can be broken up as two steps. So update to the current minimum overall minus 1 and then delete min. Right? So you can take the current value that you want to delete, reset its value so that it becomes the minimum, in which case, as we saw, when you update to a smaller value, it will propagate up to the root. And then if you do a delete min, that value will disappear, and so you would have effectively, in two steps of log n each, we would have deleted it, so overall it is log n. And now, as we just said, predecessor and successor, in a sorted list they are adjacent, so these are both constant operations. On the other hand, in an unsorted list, we have to look through the whole array. And we also said in a heap, we have to scan because there is no particular order in which the adjacent elements are stored in the heap. So what we are going to look at today are binary search trees. And in a binary search tree, we are going to argue that all of these operations are actually logarithmic, provided we maintain the binary search tree with a good structure. And also we will look at an operation called find, which searches for a value, and this will also be logarithmic. Right? So we will simultaneously be able to optimize all these 7 operations in a binary search tree. So a binary tree is just a tree with a root in which every node has either 1, 2 or 3 children. A heap was a very special kind of binary tree which we filled up top to bottom, left to right. But in general, a binary tree has no constraint. Right? So we have values at each node, and we will assume that not only do we have a way to go from the parent to the child, but we also have a way to go from the child to the parent. Right? So every node we are going to assume will have a link to its parent, left child and right child. Okay, of course these links may be missing, but if they are there, then there will be all 3. So we can point up the tree and to the 2 nodes below it on down the tree. Okay. So just in terms of terminology, the root is the topmost node, has no parent. The leaf is any node which has no children, and at any given point, if we look at a node, then it is the parent of its left child and its right child. So now we take a binary tree and we further impose a constraint on the values. So remember, like in a heap, we first had a structural condition that the tree is filled top to bottom, left to right, and then we said there is a heap property which says max heap or min heap, either a node is bigger than its 2 children or it is smaller than its 2 children. So there was a property on the structure and there was a property on the values and how they are arranged with respect to each other. So in a binary search tree, the binary tree could have an arbitrary structure, but the values are arranged in a specific way. So for each node with a value v, all the nodes below v, smaller than v, are in the left subtree, and all the values of bigger than v are the right subtree. Okay, and we will assume that there are no duplicate values. So for example, here if we look at a root node 5, then the left subtree of 5 contains values 1, 2, 4, which are all the nodes in this tree smaller than 5, and the right subtree contains 8 and 9. And now this is a property that is recursively satisfied throughout the tree. So if you look at the node 2, for example, its left subtree is just the single node 1, which is a value smaller than 1 in the tree rooted at 2. And its right subtree is the value 4, which is the right. It's a bigger than 2, the only value bigger than 2 in the subtree. Likewise, if we look at 8, then there's only one value other than 8 in the subtree starting at 8. That's the value 9, and since it's bigger, it's in the right subtree, and we have the left subtree empty. right? So we can have these kind of gaps, unlike in heaps. We can have a gap, but we have this uniform property that at any node in the subtree, all the values smaller than the node are on the left and all the values bigger are on the right. So typically we would implement this as a linked structure where we have each node with three fields other than the value. So we have a pointer to the parent, a pointer to the left child, and a pointer to the right child. So the first thing that we can do with a binary search tree is to list out its values in sorted order. This is called an in-order traversal. So an in-order traversal is a recursive traversal. It is a way of walking through the tree so that we first walk through the left subtree, then the current node, and then the right subtree. For example, if we perform an in-order traversal here, we start at the root and then we have to first walk down the left subtree. So we walk to the left child, and then once again we must walk down to the left subtree, so we walk to the left child. And now there are no left child, so now we will print out 1 and move back up because there is no right child. Now we print out 2 and go down to the right subtree. And now again, because 4 has no left or right subtrees, we'll print it out and go back up. And since we have already finished 2, we will end up at the root. Now we will print out 5, move to the right subtree. Then because there's no left subtree, we'll print 8 and go to the right subtree. And finally, we'll print 9. So it's easy to see that because of this property, we know that everything to the left is smaller than the value and everything to the right is bigger than the value. So this is like a recursive, this is very similar to the partitioning of quicksort in a sense. So we have already partitioned the values, so the smaller values are to the left, so there are bigger values to the right. And if we recursively follow this partitioning to list out, we will obviously get the values in sorted order. So now searching for a tree, a value in a binary search tree is very much like binary search. Remember, in binary search you have an array and then you start at the midpoint, and then if you find it you say yes, otherwise if it is smaller you go into the left, otherwise, or if it's bigger you look in the right. Okay, so we have a very similar thing. So we want to find a value v in a tree. If the tree is empty, of course we say that it's not there, so we return false. If the current node has the value, then we have found it and we return true. On the other hand, if we have not found it, then since we have a tree, we look to see whether the value is smaller than the current value. If it is smaller, then we recursively search in the left and return whatever we find there. If it's found there, we say true. If it's not found there, we say it's not in the tree. Otherwise, we search recursively in the right. Okay, so this is very similar to binary search. Now, like binary search, you can do an iterative version of this. So you start at the root, and then so long as it's not nil, you trace down the path, right? So if the current value is v, you return true. Otherwise, you walk down to the left, or you walk. So you start at the root, and you kind of trace a path depending on the values that you find. And then when you reach a node, you say yes. Okay. On the other hand, if you reach a point where you cannot go any further, then if you run out of nodes, if you come all the way down and then you say there is no extension where I can find it, then you will say false. Okay, so this is the simple recursive and iterative versions of find. So the next two operations that we wanted to do were finding the minimum and the maximum. So the minimum node in the tree is the leftmost node. In other words, it's a node that you reach if you go as far as you can following only left edges. So in this case, from 5 if I go left, I go to 3. From 3 if I go left, I go to 1. And then I cannot go left. There is something below 1, it's on the right. But nevertheless, since I can't go left, 1 must be the minimum element of the tree. Because everything that is smaller than something will be to its left. So if I cannot go left, there is nothing smaller than 1. Okay, so this is the reason why the leftmost value in the tree will be the minimum. Right? So we can easily find it recursively. Now we will typically use this assuming the tree is not empty. It simplifies a little bit of coding. So assuming the tree is not empty, we don't have to check any special condition and give any error when it's not empty, when it is empty. So we assume it is not empty. So if we can go left, we do. So if the t dot left is nil, then this is the minimum value and we return it. Otherwise, we recursively search for the minimum value on our left. Okay? And again, there is a very simple iterative version. We start at the current thing and we keep going left as long as we can, so long as we don't hit nil. And when we reach this point where t dot left is nil, we come out of this loop and we return the value at this point. Right? So here, for instance, we would start with 5, t dot left is 3, t dot left is 1, t dot left is nil, so this at this point we stop, so t is pointing to 1, so therefore t dot value is 1 and this is the value we return. Right? So we can find the minimum. So symmetrically, the maximum is the rightmost value in the tree. Okay? As you go right, you go bigger. If you can't go right anymore, there's nothing which is bigger than that node. So here from 5 we can go to 7 to 9, and 9 is the biggest value because the next node, which although it is below 9 in the tree, it is to the left and therefore smaller than 9. So we have a symmetric recursive solution, maxval, which checks the right. If the right is nil, then we are at the maximum and we return the value. If the right is not nil, then we recursively search the right for the maximum. And again, a iterative version of the same. We just chase pointers to the right. Right? So long as t dot right is not nil, we move from t to t dot right. And when we can't move anymore, we are at the maximum value, so we return that value. So at this point, we have done find, minimum, and maximum in a search tree. Okay, so these three operations we have done. Now, if you remember, we have to do predecessor and successor. So let's first look at successor. So recall that the successor of x in the list is supposed to be the next value, the next smallest value after x in the list. So if we printed it out in sorted order, it will be the value that would appear to the right of x. Right? And in order of the in-order traversal of a tree prints out the values in sorted order. So it was effectively what in-order would print immediately after x. So we know that the way that in-order works, right? It prints the left subtree, then it prints x, then it prints the right subtree. Right? So if we want the one that comes immediately after x, it will be the first value here, so the smallest value in the right subtree. In other words, the minimum of the right subtree, and we already know how to compute the minimum of a tree. But there could be a possibility that we want the successor of a value which doesn't have a right subtree. Then what do we do? Right? So the first observation is that if a value has no right subtree, then it must be the maximum of the subtree to which it belongs. So in this case, if we look at the value x, it has no right subtree, so it is the maximum of some subtree. So we have to first identify the subtree. So how do we identify the subtree? Well, we walk up and find out how the subtree is connected. Right? So we get to x by following a sequence of right pointers. So we follow those right pointers backwards, and when we follow a left pointer, we know that we have come out of the subtree. So therefore that node must be the root of the subtree below which this is the left subtree. Therefore that is the next value. So this entire red block subtree will be printed out in sorted order ending with x. After this, the root will be printed, which is this node which we have labeled SUCC for successor. So therefore, that is the node that we want to designate as the successor for x. Right? So here is a simple pseudocode for this. So we want to find the successor of a node t. Now if this node has a right pointer, then we just return the minimum value of the right subtree. On the other hand, if it doesn't have a right, then we need to go up and find the first place where the path turns right. Okay, so we start with t and then we compute its parent, which we call y. Now so long as this direction is right, we keep moving up. So we go to one more parent and we move t up. So that's what's happening in this loop here. Okay? So we move t and y up, and then at some point we will move t and y will go this way. So it will be y dot left, and therefore this now this y is the successor of this original node t. Okay, and then there's one special case where we reach the top and we don't ever turn right, and that's the case where we actually was started from the maximum value overall in the tree, in which case we reach nil and it has no successor, so we'll just return nil. Okay, so let's look at this particular thing. So for 3, for instance, the right subtree exists 4 and the smallest value there is 4, therefore that's the successor. For 1, the smallest value is 2, so that's the successor. For 7, the minimum value in this subtree is 8, so 8 is the successor of 7. So these all come out of the basic case where you have a right subtree. On the other hand, if you don't have a right subtree, then for instance you start at 2, then you walk up, and then where you turn right, you find that 3 is the successor. Or from 4 you walk up and where you turn right, you find that 5 is successor. Similarly, for I8, you immediately turn right, so 9 is the successor. And finally, for 9, you will come and you will reach this nil case. So 9 will say that there is no successor because it is the largest possible value. So the situation for the predecessor is symmetric. So if we have a left subtree, then the predecessor is the maximum value in this. So we go down left and then we go all the way right. Okay. And if we don't have a left subtree, right, then it means that this is already the minimum value in each subtree. So we walk back up following these sequence of left pointers until we turn the other way, and then this node where we turn is the predecessor of this. Right? So for example, if we look at these values which have left subtree, so for 5 we go down the left subtree and we find the rightmost value, which is 4. So 4 is the predecessor of 5. Likewise 2 is the predecessor of 3, and 8 is the predecessor of 9. Okay. Now we have these other values for which we can't go left. For example, we can't go left at 2, we can't go left at 4, we can't go left at 7, right? We can't go left at 8. So what do? In these cases, we start at 2, for example, and then we try to go up, and where we turn right, there we find. Okay. So we come here and we find that 1 is the predecessor. Similarly, from 4 we go, and so our goal is to go right, and then where we turn left we find the predecessor, right? So we immediately turn left at these 3 nodes, okay, and then 8 we go right, and where we turn left we find the predecessor. Okay, so this is how the predecessor works. It's exactly symmetric to the successor function. Okay, so now let's see how to insert a value. Inserting a value in a search tree is fairly straightforward. There is only one place, because of, remember that the tree is listed in order will give us a sorted list, right? So now after adding this value, it must again give us a sorted list. So it is like saying that there is only one place to insert a value in a sorted list, right? So it's like insertion in a sorted list, except we have to find the correct place in the tree to hang it, so that when we do this in-order traversal, it would be in the correct order when we list it out. And it turns out that basically we have to find out where it should be by searching for it. And if it is not present, we add it where the search fails. Okay. So for instance, if we want to insert 21, then we will walk down the tree and we will look for the place where we should find 21. So if it's smaller than 52, we go left, smaller than 37, we go left, bigger than 16, we go right. And then we find that at 28, there is no value of 21 because there's no left. So then since it should be to the left of 28, we add it there. Okay. Now for instance, if we want to insert 65, then we will go right from 52, and now at 74 we will look left, that there's nothing to the left, so we will insert it there. So it can happen at any position in the tree. It doesn't have to be at a leaf node. Like at 28 was already a leaf and we inserted 21 below it, but 74 had a right child, but we inserted something to its left because the left child was missing. Now it could be that we try to insert a value that's already there. For instance, we might want to insert 91, right? So we look for 91 and we find it. So we will interpret the insertion of 91 as something which does not disturb the tree, okay? Because we really said we don't want to have duplicate values, right? So when we insert, we try to find. If the find fails, we insert. If the find succeeds, we do nothing. So there's a very simple recursive way to do this. So first of all, we have a special case which says if the tree is empty, right, then we just create a new node and point to that node. So this is an isolated node which has only a value v. Parent left and right will all be nil. On the other hand, if we find it, then we do nothing. Now we have not found it. So now if the value is smaller than the value of the current node, and if we have no left child, right, then we actually insert. Right? If we have to go left and we can't go left, then we create a new node to our left and we make that node point here by its parent. So we create a new node here and we say that its parent is ourselves. So t.left.parent is t. Otherwise, we just recursively insert to our left. Right? So if we do have a left, we recursively insert. If we don't have a left, then we create a node with v. This is the actual insert operation, and we make it point to us through the parent. Likewise, if we do want to go right and there is no right, we insert it to the right, okay, and we make it point to ourselves through its parent. Otherwise, we recursively insert to the right. So insert is a very straightforward function. So how do we delete a node? Okay, So delete says that we are given a value v. If we find v in the tree, we must delete the node containing v. So the basic case that is very simple to handle is when the node is a leaf node, because then we can just delete it and then it just falls off the tree at the bottom. So for instance, if we want to delete 65, then we will search for 65, find it by the usual mechanism of following the left and right paths, and then since it is a leaf node, we can just remove this node from the tree and nothing happens. It remains a valid search tree. Now sometimes the deleted node might have only one child. For instance, supposing we delete 74. So we come down to 74, now we want to delete this node, but it has a right child. But now what we can do is we can promote this child, right? So we can just kind of pretend that this link goes directly through this to 91, right? So we just eliminate the node in between and we directly connect 52 to the successor of the node that is going to be deleted. Okay, so if there's only one child, then there's no problem. Now what if the deleted child has deleted node has two children, right? So supposing we want to delete 37, that is this one, right? So we identify 37. Now 37 must go, but we can't arbitrarily restructure the tree because we'll have two children and we don't know what to do with it, right? So now one strategy that works is to make a hole there to remove the 37 and replace it by either its predecessor or its successor. Okay, so supposing we identify its predecessor, but predecessor, remember, will be the biggest node, the maximum in its left subtree. So here it will be 28. So what we will do is we'll copy the 28 to this node which is to be deleted. So 37, the node has not been deleted, its value has been replaced by 28. Now why is this a valid value? Because we want to preserve the sorted thing, right? So if we have some list of sorted values and I delete something here, then what happens is that everything is to the right of the predecessor. So I basically move the predecessor to this point and I preserve the order between these elements in the sorted order. So moving the predecessor here, I guarantee that anything that is to the right remains bigger than this node and everything to the left remains smaller than this node because it was the biggest value in this. Now of course I have two copies of 28, so I must remove the 28, right? So then I'll focus on the left subtree and I delete this predecessor value. But the good thing about the predecessor value is that it's the rightmost value. Rightmost value means either it is a leaf or it has only one left child. So we are back in the simpler case, one of these two cases, right? So we can just delete the predecessor of V using one of these two cases. Either it's going to be a leaf, it just falls off, or I'm going to promote this 21. So in this case, the 21 will get promoted, right? So deleting in general consists of moving the predecessor to the current value and then deleting the predecessor from the left subtree. So it's a long piece of code because we have these many cases. So first of all, if it's an empty tree, we do have nothing to, we can't delete. If on the other hand, that value at the current node is not V, so if it is strictly less than, then if there is something to the left, we delete from there. If it is strictly greater than, if there is something to the right, we delete from there. So these are the two recursive cases, right? So if it is not strictly less than and not strictly greater than, it must be equal and we have to do some real delete. So now we have these three cases. Right? So the first case actually breaks up into two cases. If it's a leaf, it could be a leaf because it is the root, right? The root and it is only one node. So we will treat that slightly differently. So we will say that if it has no parent, that is it's the root, then deleting the value actually makes the tree empty. So we just reset t to be the empty tree nil and we return. If on the other hand, it is a leaf node, it has no children, right? Then what we do is we try to delete it by just setting the parent's value to be nil. So supposing I come here, right, and this is my leaf node and I want to delete this, then I look up and then I basically set the right pointer of this to be nil, which essentially kills off this link and says that there is no right pointer. So if the current node is the left child of its parent, I set the left child of the parent to nil. Otherwise, I set the right child of the parent to nil. So this, of course, creates some garbage because this node is now inaccessible from the tree, but we assume that this will be recovered and we don't have to worry about it. If you are doing this in a language like C, then you have to be careful to restore this back to the free space. But in other languages which have garbage collection, this will just automatically be restored when garbage collection takes over. But the point is that we are just simply removing it by resetting our parent's pointer to be nil. Right? So this is the leaf case. So having considered the leaf case, now let's consider the case where you delete a node with only one child. Right? So the first case we will look at is when we are trying to delete a node which has only a left subtree. So left is not nil, right is nil. Okay. So what we do first of all is we look at this immediate left successor. So this has a parent somewhere above it. So we first make this left child point directly to the parent. So t dot left dot parent is d dot parent. Right? Then we look up and we decide whether this is a left parent or a left child or a right child or which parent. So supposing the node we have, okay, is sitting to the left of its parent, if t dot parent dot left is t, okay, then what we do is we make this point directly here. Okay. Now on the other hand, if it was not like this but it was the other way, right? So if this happened to be a right child of its parent, then we say that t dot parent, the right child should now point directly here. Right? The right child of the parent is now my left child. Right? So this is a way to splice out or remove this thing and promote the child, the only child up. We do a symmetrical thing if it's only the right child. Right? So so we first take the right child and then we reset its parent to be your own parent, and then after that, depending on the case, we either make this point like this or this point like this. Okay? So either t dot parent dot left is t dot right, t dot parent dot right is t dot right. So if we have only one child, we just remove the node effectively from the tree. And finally, if we have a node with two children, what we do is we first compute the predecessor of v, okay, and then we set the current node's value to be the predecessor value. And now we know that this value is duplicate, so we go to the left child and delete it. Now remember that when we delete it here, the left child, we are deleting what we know is the maximum value. So therefore it will have either no children, it will be a leaf, or it will have a single child. So it won't come back to this case, it will just stop at the earlier two cases and it will get successfully deleted. So there is no problem with just calling delete again. Right? So all these operations that we have described now walk down a single path. So therefore, the worst case complexity of any one of these operations is the height of the current given tree. And if we have maintained some kind of a balanced tree like a heap we saw, then the height is logarithmic in the size. So if we have n nodes, the height is order log n. So we will see in the next lecture how to maintain the balance, but assuming that we maintain the balance, we have succeeded in what we achieved, what we wanted to achieve, which is we wanted all these 7 operations, okay, to be simultaneously efficient, and they are all now log n time because each of them can be achieved in one traversal up or down a path in the tree.